Okay, so yeah, this image here, I mean, it's supposed to capture something about the tangent plane. And I'm going to write down the general equation for a tangent plane. We sort of talked about it in class on Friday, but I want to talk about the general equation for a tangent plane, and then I want to also talk about this approximation using the tangent plane to approximate the value of a function. Okay, and then we're going to start talking about directional derivatives, which are also cool. But let me just, yeah, this is on the handouts page, this most important image. But let me stop the share and just go to the Blackboard. So, all right. This is gonna be fun. Ow. All right. So, right, we sort of got into the tangent plane stuff a little bit. We definitely got into partial derivatives, right, in class on Friday. And yeah, the tangent plane. So this is one equation. We're going to see a different equation for tangent planes in a probably by end of this week or next week. But what we've seen so far is that, planes in general, well, again, we've seen different equations for planes in general, but so here I would say non-vertical planes, because remember I did the whole thing about if you want a vertical plane, you have to give a more general, an even more general equation. But you've seen something like this, right? This is like the point slope version, I called it. Right, where m is the slope in the x direction and n is the slope in the y direction. X naught, z naught, x naught, y naught, z naught is a point on the plane. M is the slope in the x direction. And n is the slope in the y direction. Okay, so that was kind of our first equation of a plane, right? And then I guess what I want to say is for tangent planes, for the tangent plane to z equals f of x, y, at the point a comma b, let's just say, I could say x naught comma y naught, I guess, but a comma b. Well, what do we know, right? So we can basically plug these in for here, right? So x naught is a, y naught is b, right? Just by kind of how we're given this. A, y naught is b, z naught is the function value, f of a comma b, right? We just plug in to get the height. M is the partial x at a comma b. And n is the partial y. That's the thing. It's like we've found that this slope, we understand slope in the x direction, slope in the y direction. Those are just the partial derivatives when we're thinking about a function, right? By the way, I'll try to watch the chat. If remote people have any questions, please stick in the chat. Hopefully you can hear me. Okay, right, so these are the ingredients that go into this. So what you basically get is you get this equation when you plug it all in. We get z minus f of a comma b is, I like to put parentheses around this just to think this is actually a number right here. That's a number times x minus x naught, sorry, x minus a, right? That's a minus sign. And then this is a number times y minus b, like that. So that's the equation. That's sort of the general tangent plane equation. And sometimes you see the f of a comma b moved over to the other side, like just z equals, right? Trying to give a general z equals. Does that make sense? Let's do an example. It's a function that I think is somewhat nice. Well, maybe not that nice, but I can at least find a nice point. F equals the square root of x squared plus y cubed, and the point is 1, 2. Okay, let's make it -1, 2. Doesn't matter too much. -1, 2. Right, so this is A and this is B. So maybe take a minute, talk to the people next to you, around you, compare notes, try to figure out all the numbers that go into this and write down the general tangent plane equation. Okay. So you're going to try to fill in this. But definitely check with your neighbors. I'm going to pull up some Mathematica. And then we're going to check our answer. I'll show you the surface. We can actually look at the tangent plane and see if we get something tangent. So are you checking with the people around you to see if you're getting the same thing? Turn to one of your neighbors and say hi. Whoa. Actually, negative values of z shouldn't even be a thing. Huh. Make the y a little more narrow. Yeah, can you do these derivatives? Partial derivatives? This is a weird ass looking surface. Yeah, when you do equations, sometimes this is a Mathematica thing, which I mean, I think this is right. It's just strange. Yeah, sorry, let me show on the Zoom too. That's your surface. Hopefully our point, you can actually see the tangent plane. It has issues when you get down close to 0. I guess if y cubed is negative x squared, then you get 0 because y cubed can be negative. Anyways, it's interesting. I would not have guessed this is what the surface looked like. But okay, so I've given you a couple of minutes. So Yeah, so did you guys do your partial derivatives? First off, what's this value? It's a nice value, right? So so f of -1, 2 is 3. What's the partial x? You have to do the partial x in general, right? And then plug in the point. So somebody tell me what they got for the partial x. Oh yeah.
Why is it not plus or minus?
Well, the function is the square root. So it's when we do a function, it usually just means the positive square root. But I mean, it's a fair point. Like, yeah, well, if you just see a square root sign, you're supposed to assume it's the positive square root. Okay, so what about partial? Who found the general partial x? Someone tell me what they got. Behind you, yeah. X over the square root of x squared plus y cubed in general. Oh, did you plug in 2 and then do the single derivative? Right, okay. So is that right? Because this is the 1/2 power. So when you differentiate it, you get a 1/2. But I see some looks of consternation, so maybe I should just remind you of, like, I think that's right, but it's like, so it's the derivative with respect to x of x squared plus y cubed all to the 1/2 power, which we can think of as 1/2. Remember, it's the chain rule, right? It's 1/2 blah to the -1/2. That's a power rule times the derivative of the inside. This is another reason I like the d over dx notation, because you can use it to unwrap chain rules layer by layer. Right, that this is what the chain rule says, is we have blah to the 1/2 power. Blah to the 1/2 power is 1/2 blah to the -1/2 power. And then times the derivative of the inside. And so that's just a 2x. Right, so you get 1/2 x squared plus y cubed to the -1/2, which is 1 over the square root, times 2x, which is x over root x squared plus y cubed. I asked for honesty. Who did this? Who got this? Who did this right? Some people shaking their heads. Appreciate it. Does this sound familiar though? Chain rule stuff. Right, and then so at 2, 1, or 1, oh, sorry, -1, 2, what do you get? We already know that this bottom is 3, right? 1 squared plus 2 cubed is 9, so it's just -1/3. And then similarly, what's the partial y? Well, the only difference is we're going to get a 3y squared here. Is that right? So it's, did you guys get 3y squared over 2 square root of x squared plus y cubed? Nods. Okay. 3y squared over 2 root x squared plus y cubed. And so when you plug in the point, what do we get now? Oh, something nice still, right? 2? Yeah, the bottom, this square root becomes 3, so the bottom is 6, and then 3 times 4. Okay, even nicer than I thought it was going to be. Yes. Oh, the 1/2 is out here in front, so it cancels the 2. Is that what you're asking? Like we picked up this 1/2 from this derivative. We picked up the 2 from this derivative. And they cancel out? Oh, I see. Is that what you're, okay, yeah. Yeah, good. Yeah, okay, so we get the equation z minus 3 is -1/3 times x minus negative a, which I think is x plus 1, plus 2 times y minus 2. And if you like, you could sort of, write this out just to get a nicer form, like, so z is -1/3 x plus 2y. What do we get? This becomes -1/3 minus 4 plus 3, maybe -4/3, like that. I just did some arithmetic. I might have done it wrong. Someone's nodding at least, so that's appreciate that. So I think maybe this is the tangent plane. But I mean, this is perfectly good answer too. And it conveys information about, the point and the slopes and stuff. So I was going to say, let's put it in. Let's see. Let me share screen again. Let's put it in and see if we get something that's actually tangent. So I can put another c equals -1/3 x. I can't see this. Plus 2y minus 4/3. Okay, so let's try it. If it's wrong, it'll jump out as being wrong. Ooh. I mean, feels fairly tangent, right? Looks a little weird. Not sure why it's being cut off. Well, okay, I see why it's being cut off, because it's running into the edge of the. It looks like, I mean, I could probably zoom in, but it looks like that looks tangent maybe. The point, where's the point? -1, 2. I guess it's slightly over. Like that's x equals 0, so x equals -1 is like there, and y equals 2. So yeah, I mean, I could change the window to be something like, I could have just go 1 unit on each side of the point, like -2, because that's x equals -1, y equals 2, so I could go from 1 to 3, and z equals 3, so I could go from like 2 to 4. Should maybe jump out a little more if we zoom in. That is actually tangent. It's almost like it's trying to show through right there, which makes me a little worried. But I think that works. Yeah. Okay, so we have tangent planes. All right, so that's good. You can find the equation of a tangent plane to a surface. I guess the one thing I would just to tease something to come ahead is that, like, we'll also talk about when you can't isolate z as a function of x and y. Like you have a surface, but you don't have z in terms of, you don't have one of the variables in terms of the other two. You're gonna have to think about how to find, there's a nice way to find the tangent plane to such a surface also. If you go down a dimension, it was like finding the tangent line to something that wasn't given by a function. Like if you had a circle or something and you wanted the tangent line at a point. There was a way to do that. Single variable calculus. Try to remind yourself. But yeah, okay. So now the next thing, I guess the next thing I wanted to talk about, now this most important image thing comes into play, I think. So let me just share that. So this is, right, this is something like what we were just looking at for the specific example, where you have a surface, the curvy thing up here, you have the tangent plane there. And I do want to talk about this expression because it's important. And you can sort of see it already from the tangent plane equation. If I bring the tangent plane equation down for a second, you could think of this as a delta z, right? This as a delta x, and this as a delta y. And so this is actually a function of two variable version of something you've seen as functions of one variable. So One camera. Yeah, you can kind of see that. All right. Yeah, so if you were, I want to talk about what's called a differential. And it's a thing that lets us approximate values of functions. So did I just erase the thing we just did? Why did I do that? Didn't mean to do that. I meant to erase. Sorry. Oh well. Apologize if you're behind on the, at least it's on the recording. I do that sometimes. I try to erase the other board. So, right, but at least we had the equation for the tangent plane. So, yeah, so differentials. So we can rewrite so let's rewrite the tangent plane equation as delta z equals the partial x times delta x plus the partial y times delta y. Okay, and think of that, right? We can think of it that way. And when you look at the right, sorry, that's what I wrote on the board for those of you who, if you're remote. If you look at this picture though, so you can sort of see it in this picture too, that like, if I'm going from this point, a comma b, to this point, x comma y, in the xy plane, I'm moving delta x and delta y, right? So I change in x and change in y to move from a comma b to this point. And there's some nice geometry here that you can sort of see. There's triangle. There's kind of a triangle right here, right? And this is basically the change in z if you go in just the x direction. Because this is the slope. This is the slope. This partial x right here is the slope in the x direction. So slope, and slope is like rise over run. So this is like slope times run equals rise. Right, so the change in z there from that contributed from that. And then if you go in the delta y direction, you could almost draw in like another triangle here, or down around in the back of this picture, there's a triangle. So the contribution, and they have it sort of labeled right here. So the contribution if you go in the y direction is partial y times delta y. And so the total change is actually just the sum of the two changes, the change in the x direction and the change in the y direction. So it's sort of nice, and it comes from the tangent plane equation, but it's also, you can also sort of see it geometrically, that if you follow this, right? And so let me just go down a dimension for a second and just remind yourselves of what this is. Go down a dimension. Y equals f of x. We have like basically that f prime of x is approximately delta y over delta x for delta x small. Right? And I could rewrite that as delta y is approximately f prime of x delta x. So this equation you've seen. This is following the, well, so that I have an approximation here and I have an equal sign there. So I have to be a little bit careful. This is following the tangent plane. If you follow the tangent plane, it's an equality. It's the same thing over here. Let me just draw a picture. If we have like a function, you know, like that, and we have the tangent line like that, and here's our, you know, here's our delta x right here. Then you have this thing of like the delta y following. So there's this point and there's this point, right? So there's a change in y following the curve, and then there's a change in y following the function. There's like two different changes in y. You see what I'm saying? Like there's a change in y following the tangent line, and then there's a change in y following the curve. And so you have to be a little careful how you write this stuff. Like it's almost like, which delta z do I mean? Which delta y do I mean? Do I mean following the function? Do I mean following the tangent line? And so I'm actually, what I really kind of want to do is say something like this. I want to change that to an approximation. So this is like following, yeah, this is like, so this is y equals f of x. This is the tangent line. Down here's delta x. This I want to say, this is delta y. Right? And so we can approximate values on the curve by instead following the tangent line. So this, it's almost like the right-hand side of this equation is like following the tangent line. And the left-hand side is following the curve. Following the curve of the function. So they're not exact, but they're approximations, right? This right here, this right here is f prime of x times delta x. Right, just because it's the rise over the run of the tangent line. Does that make sense what I'm writing? What I'm saying? Yeah, I should zoom in on this. It's gonna be a problem, probably. Ooh, hello. Yeah. So that's the picture I was drawing, and then actually fit that into. Okay, so right. And so that's just an interesting thing to think about. It's like we can approximate changes on the function by changes on the tangent line, right? And zoom back out. Okay. And then if we go, and so this is supposed to be, this picture here on the screen is supposed to be the analog of that picture I just drew. Does that make sense? And you could also think, I guess back on the picture on the board, you could think of the two heights. I could label the two heights similarly, these two blue points, I could label similarly as the true value of f at that point versus the approximation, the tangent line approximation at that point, right? Okay, now, so I guess what I want to say is you can use this to estimate functions near points. So, but I also want to say there is something, so I have these approximations, right? These I'm giving as approximations. Like I'm not drawing an equal sign, I'm drawing a squiggly. You will see stuff written like the following. You will see like, you will see an equality, but you'll see it with d's instead of deltas. And that's what's called the differential. But I guess, again, you're just supposed to think that in some ways, both sides are following the tangent line, or maybe the thing to think about that I haven't really said so far is that the smaller delta x is, the better the approximation is. Do you believe that? Like the whole idea is that in the limit as delta x shrinks to 0, the approximation becomes an equality. I mean, both sides become 0 in some sense, but like, you know, and then there should be something similar here. So, so the differential, which I haven't said yet, is you would write something like the following: dy is f prime of x dx. So instead of having an approximation, you have an equality, and you actually write dy and dx. And this is somewhat the inspiration for the Leibniz notation, where you write the derivative as dy over dx. And so you'll just see this written sometimes. And really, this is following the tangent line. So it's funny, up in that picture, and there's a picture like this in the book, I kind of like this interpretation. We have our like X and Y axes, right? But then we have this point. I'm going to kind of draw the picture up there again. We have this point on the graph that we care about. And what the book says, and I kind of like this interpretation, is like, you almost think of this as a new set of axes right here going through this point, where this is like the dx axis, and this is labeled the dy axis. This is like zoomed way in. Think about zooming way in. Zoom way in. And so really what you have is this yellow curve. You've done that on your calculator, right? You've zoomed in on a function and it like straightens out. It kind of becomes this tangent line, right? So I think this is kind of a neat way to look at it, that like if you zoom way in, the yellow curve straightens out. And so you kind of just have like something like this, where that's supposed to be a straight line now. And I have my like dx axis and my dy axis. It's almost like I'm forgetting, it's like a relative position thing. Like, you know, the origin is an arbitrary. There's no point in space that's the actual origin, right? And so you might think, well, where I care about is actually where I am right now. So if I zoom in where I am and make that the origin, then what's the equation of a line through the origin with these axes? Yeah. Yeah, well, so the variables now are dx and dy. And whatever slope this is, it's basically, you know, what's the equation of a line through the origin on the normal, yeah. Yeah, I mean, it's a constant, but if you want just a line through the origin, it's like y equals constant times x, right? So you're saying move the x down. But it's like just y equals constant times x. You don't have to worry about the y-intercept or anything. It's just y equals mx, right? And so that's supposed to be what this is. This is like slope f prime of x here. And so that's what this is supposed to represent. I mean, it's kind of just a conceptual idea of like, let's have a new world where like we've made this point that we care about the origin, and we label the axes dx and dy, and then we have something like that, right? I kind of like that. It's kind of a nice way to look at things. So back up in 3D. So similarly, in 3D, we could write dz equals f sub x times dx plus f sub y times dy. And it's like if we zoom in on a surface, we can actually think of like, again, making, this is the equation. If you think of this as a new x, y, and z axis, this is the equation of a plane through the origin, right? It's like the plane equation, but with x naught, y naught, z naught equal to 0. It's like, this is my new x, this is my new y, this is my new z. And so it's almost like a frame of reference thing. It's like, okay, well, I've got dx, dy, dz, and I'm not going to be able to draw a plane to the origin very nicely. But you can imagine, I can't draw a plane to the origin. Not in a nice way, not nicely, not as nicely as this. But you can imagine that there's some plane through the origin. I almost want to have like an x and a y. That's not good. All right, well. I'm supposed to say like somehow that's a plane and it's like passing through the origin. But you can, so it's like a new frame of reference kind of. But this is really just a conceptual thing. I mean, it's, but I sort of like the idea, like that's something you do in physics a lot, where you like change your frame of reference and, you know, look at the observer's point of view or something like that when you're doing like special relativity. Or, yeah, and The point is, though, is that the thing that I was going to say that you can actually use this for is to estimate values of functions near points. So we can use the differential to estimate. And we could have just done everything in terms of that approximations, but I don't know. People like to write things this way. It's kind of a nice way to think about it. Estimate function values. Let me just give you an example. Values. So here's an example. So let's do the same function we had before. So z, or f of xy, is the square root of x squared plus y cubed. And if I say estimate f of negative 0.99, 1.98. Okay, this is the kind of thing. It's like, this is a point, this is close to negative 1 comma 2, right? This is close to negative 1 comma 2. And we know what's going on at negative 1 comma 2. We figured all that out already, right? And the claim is that, like, right, if we just want, we're changing x and changing y a little bit. Like, we've changed x away from negative 1 a little bit. We've changed y away from 2 a little bit. And we want to know and we know the value of f at that point. So if we use this differential to find the change, to estimate the change in z, then that will give us estimated change, which we can add to the function value to get the estimated value. Right? It's sort of like that picture going from the height of the given point a comma b to the point x comma y. So let's actually do that. It's not too bad. So hopefully you sort of see where I'm going with this, but so the idea is use the differential. So for this function at this point, we know that the partial y, the partial x was negative 1/3. Was it negative 1/3? Positive 1/3, negative 1/3. And the partial y is 2, right? That we found. So if we write dz is partial x times dx plus partial y times dy, that's really negative 1/3 dx plus 2 dy, right? So that's what the differential is here. And we move from negative 1 comma 2 to negative 0.99 comma 1.98. So what's delta x? Or the change in x is delta x, although we're gonna use dx. So the change in x here is really our dx, which is plus 0.01. We go from negative 1 to negative 0.99. So that's plus 0.01, and the dy is minus 0.02. Is that right? Going from 2 to 1.98. Maybe I should use fractions. I don't know. So then we can find dz, right? Then dz is -1/3 times 0.01 plus 2 times -0.02. I'm just plugging in to this equation for the dx and the dy to get the dz. I have a mixture of fractions and decimals, which is bothering me. Should make them all decimals or something. This is -1/300 minus 4/100, which is -1 minus 12 minus 13/300. Something like that. Is that right? Okay, so the change, if we move just a tiny bit, yeah, if we move a tiny bit in that direction, we get, yeah, I mean, I guess this is probably something like -0.0. I mean, if I just think about adding these together, or 3 repeating. Is that right? I mean, it's definitely -0.04 from this and minus another third of a 0.01, which is like the 3 repeating there. Yeah. That's right. It's only really good. I mean, it's kind of a funny thing because it's kind of hamstrung by this idea that it works if we're estimating close to a point we understand really well. And we understand really well what's going on at the point -1, 2. So, right. And so that means then that we can actually estimate, we haven't estimated the value yet. We've just gotten the dz, the change. We've just estimated the change in z. And so, so what we can say is that dz is really approximately the difference, right? It's the difference from the point we know to the point we care about, the point that we know versus the point we're trying to understand. And if we do that here, so, right, dz is basically, well, I should say this, f of, I forgot the point, what was it, -0.99, 1.98 is approximately f of -1, 2 plus dz, right, the change in z. But we know that this is 3, and we know this is -0.043 repeating. So that means that this is approximately 2.956 repeating. I think I could do it in terms of fractions, but it's probably right. Okay. So that's an approximation. Right, you see what I did? I just added the dz to the height that we were at height 3. And we're just adding the dz. Of course, we can ask a computer to check for us, right? So what's actually the square root of -0.99 squared plus 1.98 cubed? Let's ask. Let's ask the Google search bar. Let's ask our friend, the Google search bar, to compute for us. Will it compute that for us? Should we go to Wolfram Alpha instead? Let's try it. Square root of negative. I mean, it's kind of interesting because we did all that by hand, right? We didn't do anything with the computer, and yet we should hopefully get something close. Hey, not bad, right? I'm impressed with us. Right? So it's actually, so this is, I guess I should say 6666 going on. And this is, the actual value is 2.95677. So we did this by hand. This the computer told us. I feel pretty good about our abilities. Nice. Okay, so that shows you the sort of like the usefulness of the differential. I mean, by the way, how does the computer know this? It's really using, this is a first order approximation, like you use Taylor series for higher order approximations. And so it's really probably just using the Taylor series of some high degree of approximation to give a good answer. But I think 3-digit accuracy is pretty good. Okay. Yeah, makes sense. Okay, the one other thing I want to say, might be worth saying here, is just to tease Wednesday, and I think I might have even teased this last Friday, is that like we can also use the same ideas. We don't really write in terms of differential, but we can use the same ideas to estimate the derivative in any direction, not just the x direction or the y direction. We can say, let's move. I mean, this could give us an estimate of the derivative in, if you think about it, the like delta x was 0.01, the delta y was negative 0.02. So like, again, if you actually think about this dx, dy, dz sort of axes, it's actually kind of a nice way to think about it. That's like saying, let's go over 1 and down 2. So that's like that, if we go like over 1, down 2, it's like that direction, right? And we actually estimated, yeah, this is the vector, because we got the delta x was 0.01 I plus negative or minus 0.02 j. And so we found the change, we estimated the change in that direction. This direction. Actually, we could even estimate the slope. What about slope? Because that's kind of what we would like to be able to estimate the slope in any direction. So that would just be the change in z over the change in sort of like x and y. Kind of goofy to say. But it's like now we're moving from the point, what was it, -1, 2 to this point in that direction. And this is just going to be the horizontal distance, the distance traveled, which is the distance in the xy plane, right? So this is going to be delta z over the xy distance. In fact, I think I said last time, there's a problem set problem that sort of teased this. So we have an answer here. We have negative 0.043 over the distance, but it's like the magnitude of this vector over the magnitude of this 0.01 I minus 0.02 j. And so that's some number. I don't really want to compute it, but I'm just trying to give you the idea. It's some number, right? This is something you can compute. It's just a square root of this squared plus this squared. I mean, I could get an actually pretty exact answer if I wanted. But yeah. So this could be the derivative in the direction, but I'll just say slope. It's a slope in that direction. Okay, does that make sense? So what we're going to do on Wednesday actually is we'll look at a point, a function. We'll do an easier one, but we'll look at a function near a point. I'll have you guys actually take a bunch of different directions and compute the slope. And then I claim there's an interesting pattern. You can actually find the slope in any direction now called the directional derivative using this idea. But there's a nice pattern in how to compute that. So we'll do that. Okay. Yeah, I've got a bunch of office hours this afternoon, tomorrow afternoon. Like I said, if you're still working on the last problem set, come talk to me. Come either send it to me if you finish it or come ask questions. All right, thanks everyone. Thank you. Yep, take care.
Thank you.
Thank you.